Hey, it's N. Okay, so today I'm going to be doing a crash course in GCSE chemistry calculations. I've only got one person, I think, waiting, which isn't great. We've got Yeehan. Hi, Yeehan. Thanks so much for coming along. I'm kind of hoping that more people will join us. Okay, but I'm going to go straight into it because I want to keep this as short as possible. I know you guys are all on holiday. I hope you guys are having an amazing break. And let's see if we can run through our calculations. Now, for my year 10s, and you guys know who you are, you guys have got your test first lesson back. So as I said, what I was going to do is I'm going to do a complete run through all the types of calculations. I'm going to bring it straight back to an exam paper, show you how nearly all types of calculations are done in most exam papers. This includes the students who are doing dual science. So those dual scientists in the room thinking, well, it's not going to really involve me. It really does. I'm actually only looking at a paper 1 today. But I just wanted to kind of show you where those questions are and how most types are done. And it also gives me an opportunity to show you that we can identify the types of calculations that are being asked in terms of when you're actually sitting the paper. Being able to do that identification is a really useful thing. Okay, right, let's see if I can get this up and running. So, okay, I'm going to share my screen with you guys. There we go. I'll do entire screen, select that one and go. Right, okay, guys, so, that should not be running. Let's get rid of that. Okay, so my usual thing here, folks. By the way, I do have the chat window open. I'll reply in words rather than in texts. Okay, so we're doing a complete run through of all the calculations here. I'm going to be as quick as possible so you guys can watch this back and keep it relatively short. Yeehan, or in fact anybody who's watching this, I need you to do me a favor. If you can tag the video as we go through it with the different types of calculations that are done, that would be really super useful. This was one of the feedbacks I got from my year 11 from last year. If I could tag the webinar video as I go through at the different points, but I think I'm not entirely sure how to do that yet. So I'm definitely going to be asking for some support from you guys with this one. Okay, so my learning objectives, I want to go through all the different calc types that you guys are going to be sitting at GCSE, and there are 10 of them. Now, these 10 types will support you all the way through GCSE and into A-level. So it's a really useful, I'll put times 10 actually on that one because it's quite a useful thing. Times 10. There are 10 of different types of calculations that you're going to be doing just within the moles kind of area of chemistry. There are additional calculations which we do, which I won't actually visit in this webinar, but I'll hopefully cover those in other ones. We can use timestamps. Yes, Yeehan, that would be super useful. If you can timestamp this, if you just make a quick note on a piece of paper with timestamps, then I can add in the timestamps after I've done it. That would be perfect. You're a star. Okay, next one is be able to recognize calculation types from exam questions, and the third one is excess reagents. Excess reagents for my year 10s. This one might be useful for you. I covered it very, very, very quickly at the end. We rushed through the calculations topic in order to fit it all in by the end of the year, and it was really tough. And I briefly went over excess reagents with you guys, but I thought I'd do it and focus on that one. Okay, so first thing I wanted to do is, for those students who don't have me as a teacher, it's often really, really useful to list down all the different types of calculations that you sit at GCSE. As I said, there are additional ones in other topics. Relative atomic mass calculations from percentage data from mass spectrometry, Q equals MC delta T, enthalpy calculations from thermodynamics. These ones are other calculations, but I'm focusing today purely on the calculations of moles and where it's used in chemistry. And these are your 10 types. Now, technically, it's more like 12 types if you take into account the moles section and how it's divided into 3 different types. But this is in order of how it should be taught, in my opinion. So we start off with relative atomic mass. This is relative atomic mass, RAM, and this is relative molecular mass. This is relative molecular mass. Now, most of the time they're short forms now to A, capital A and a subscript R and capital M subscript R. standing for relative atomic mass and relative molecular mass. But these calculations where everything starts. And I'm just going to really quickly give you some examples of these as we run through them. So ARs and MRs are very straightforward. So the first one, if I just go, I'll do the EGs here, EG. So if I go magnesium for relative atomic mass, we get this from the periodic table. And of course, we know that each element has two numbers. And the top one is the mass number. So that one's the one there. I'll try and color code this as well. So this one here ties into relative atomic mass, and it comes directly from the periodic table. Then we come across relative molecular mass. Now, of course, molecular mass, I'm just going to put a double line in there, would be something like magnesium oxide. Now, I am going to mention one more as well, which is RFM, relative formula mass. Now, there is a difference between the two of these. Relative formula mass is for ionic compounds, whereas relative molecular mass is for covalent compounds. Now, in reality, of course, the calculation is the same. It's the reason why I have to teach it is because students often get freaked out if they see a word they've never seen before. And to see RFM can often spook students. So technically, this question here would be an RFM. Hey, Hibber, thanks so much for coming along. It's really nice to see you. Thanks for coming. So to calculate RFM, of course, the RAM for magnesium was 24. There's our answer. The RFM, because this is an ionic compound, would be 24 plus 16, and this is the atomic masses of the two elements. We know that they're bound together, so the total mass of that would be 40. So there's that one. That's relative formula mass for ionics. But it's exactly the same thing if I switch to something like methane. That would be RMM, because it's a molecule. Because it's covalent, they travel around in single units called molecules. Definition of a molecule, a substance made of more than one atom chemically bound together by a covalent bond. And this, in case, is going to be 12 plus 1 times 4. It's nice that most students, of course, short that just as 12 plus 4. It's a bad habit, really, but it's not really penalized because the answer is where the mark is. So in this case, the answer is going to be 16. So this is relative atomic mass and relative molecular mass. Really straightforward. It's like the beginnings of the calculations. Very straightforward, not too complicated. Then the next one that we do is we drop into formulae, of course. Formulae, of course, is how we know what the formula is for each substance. So, for example, how do I know that magnesium oxide is MgO and not? I'll put a slash in there, and not Mg2O2 or MgO2. How do I know that this one's the correct one? And of course, that comes down to our charges. We get our charges from the periodic table, from their group numbers. We've got magnesium 2 plus and O2 minus. The charges are going to cancel out, so the correct formula is MgO. You can often use the cross and down trick. Teachers often teach this as the X factor. I really don't appreciate it very much, but that would be Mg2O2, but of course the numbers then simplify down. So this is formulae, and formulae does require practice. Students really don't see it very often. As an individual question, it's often incorporated, of course, into the equations, which is, of course, what then follows. So equations, of course, is just simply usually being either, these questions are subdivided, either the total creation of an equation, so total creation, often a translation from word to symbol. That's the most common form at GCSE. At A level, they tend to not give you the word equation at all. They'll just put it into a sentence and require you to create it in its entirety. But the equation also, of course, is, rather than total creation, it'll be provide products. That's, of course, again, same thing. Now, I'm hoping that all of you swap and drop. I like it. I'd love to know which teacher teaches swap and drop. I like that. It's kind of nice. Yeah. I'll provide product. So provide products. So this one, of course, is the question simply giving you the formulae or the words of what's going in, and they ask you to give the products coming out. You'll see that in the exam question shortly. Alternatively, it could be reversed as well. It could be provide reactants. Actually, that's actually surprisingly a bit more tricky to provide reactants. Again, same thing though, but this, I'm hoping that all of you will realize that the equation, these two are inherently linked. Without formulae, you can't build equations in this channel. Cool, thank you, Jens, nice to know. Formulae and equations, they go together. Without those two, you can't do each one of them. Equations relies on formulae. Okay, next one, of course, is percentage composition. Let's look at the classic one, of course. Percentage composition is looking at how much of a compound is made up of different elements or pieces. So the example here would be calcium carbonate. And they would ask you what is the percentage, perhaps, of calcium, percentage calcium. And this is, of course, it's what you want over the total. So in this case, we know that calcium weighs 40, carbon weighs 12, and oxygen weighs 16, but there's 3 of them. So the total, by the way, this is ionic, so it would be RFM, would be 100 as an RFM. The percentage of calcium would be 40 over 100 times 100, and that would give us 40%. I use limestone because it's one that comes up a lot at GCSE, and it's a lovely one because people often do it inherently. They can often see the 40% in the numbers. Hey, Sian! Finally I can comment. Hello, Mr. Duncan. Sorry I'm late, Vadmik. No, thank you so much for Sian for coming. I appreciate it. I've now got 3 people. Yay! Whoop, whoop. Okay, back to percentage yield. Now, of course, the calcium one, if I've got to be careful. As a chemistry teacher, you learn when things cause trouble, and this is one of them. I've got to be careful because the calcium is very straightforward because there was one of them. Whereas if you do, this was the percentage of calcium. Whereas if I was doing the percentage of oxygen, then that's a bit more tricky because I need to do 16 times 3 over the total of 100 times 100. So 48%, that's not right. 48%. So that one's a bit trickier. It's just, again, it's something that requires practice. It's very straightforward in reality. I do want to give one more example, and one that seems to be appearing more and more these days, which is, we know copper sulfate can be anhydrous or hydrated, and this keeps appearing. This compound, by the way, which is bright blue, that's blue, the hydrated one, that's a 5, by the way. That's bright blue, it's a beautiful blue, actually, one of my favorite blues. More colors, see if I can find the blue one. It's a beautiful blue, quite dark. Yes, look at that, beautiful blue. And this one, of course, what they'll ask is, what is the percentage of water? So that one's, of course, a bit more tricky. So again, you still have to find out the total, 63.5 for copper, plus 32 for sulfur, plus 16 times 4 for oxygen, plus water, which is 18, oxygen, of course, which is 16, hydrogen, which is 1 times 2. So the total for water is 18, and there's 5 of them, plus 5 times 18. So if I want to work out the percentage of water, I would do 5 times 18 over the total, which is something like 249.5, something like that. Let's just quickly run through that. So 63.5 plus 32 plus 16 times 4 plus 18 times 5, 249.5. So over 249.5, the total of all that, that's 249.5. The total for the waters themselves is 18 times 5, 18 times 5 is 90, of course. So we've got 90, I'll erase that, 90 over 249.5 times 100, and I'll get 90 divided by 249.5. 90 divided by 249.5, come on calculator, times 100, so it's 36%. So these kind of questions seem to be appearing quite often now with these hydrated salts, and they keep throwing in all kinds of ones. That one's the most common, but there are many different hydrated salts with different quantities of water. So these do appear a lot. It's definitely worth having a look at. Okay, so percentage composition's done. It's nice to run through the calculations type as I skip through them. So I've done the first 4 now. Then, of course, it drops into the most feared. I think that's the right word. The most feared part of calculations, which is moles. I really don't know why. Moles are just the most wonderful thing. They really do make me happy. They're furry, they're cute, you know. But moles is a very straightforward thing, and there is a definition for mole. The total number of particles in 1 mole of anything is its relative molecular or atomic mass in grams, which is quite useful to know. But moles is simply, to put it simply, it's a way of counting particles, and my students would know this. I make a very big deal of this. And what you'll notice is I've broken it down into the 3 different types of moles calculations that you're going to see. We're going to see solids. Now, you'll notice that I put solids, liquids, and gases, but then underneath I then put gases in solution. The reason being is the solids one, I like to teach it as solids, but it's not entirely accurate. It is anything where you're provided with mass. So we can have 10 grams of a solid, we can have 20 grams of a liquid, and we can have 50 grams of a gas. If they're providing you, and the key thing here is, of course, is the unit. if you're given mass, then you're working in a particular moles calculation, and our calculation, of course, is a number of moles is grams over grams. Anybody who has me knows that I do this. Harry, thanks for coming along. Hello! I literally just said what Harry said on the chat, by the way, which is lots of those. So we've got anything where they're provided with mass. I like to teach grams over grams. Some people prefer mass equals Mr. Mole to rearrangement. I don't particularly like it so much because it doesn't have moles as the subject of the formula. But grams over grams is the way I teach this. So there's our first equation. And I should actually make a point of this, which is the whole point of a mole. What does a mole do? Moles counts particles. And this, if you can get this very clearly into your mind, it really does help, because there are so many times in chemistry where we're wanting to count particles in equations. That's why we balance them. I'll come back to that in a minute. But moles count particles, and what I'll do is I'll refer back to that as I walk through the calculations. So we've got our first calculation type. Now, for those students who like to use triangles, please don't. I'm not a fan of them. I know there are many teachers who are. And I won't name any names, but there are teachers who are a fan of triangles. I'm not. You need to learn in chemistry how to rearrange equations. It's simple mathematics. It's year 7 maths. And it's worth practicing it in the chemistry context. I think often students get confused when calculations appear in chemistry because they feel like they don't understand the context. And rearranging equations is good practice, and it gives you a better understanding of what you're doing with the numbers. Okay, the gases. We then get a second equation for gases. Now you'll notice that I'm using the symbol N. N is the symbol, lowercase n for moles. And you'll notice that I'm always having my equations set out to have that as the subject of the formula. So moles equals V over 24. Now V over 24 is dependent on that you're in decimeters cubed. There is an alternative to this because, of course, the chemists, a liter is an awful lot. It's a big, big quantity. And a lot of the time, we don't really deal with liters. It's an awful waste of chemicals. So we tend to deal in centimeters cubed. And most students who've done any practice papers will see this, because what happens is they see that they'll say, a student does a chemical reaction and collects 20 centimeters cubed of gas. You're not going to collect a liter. I mean, God, trying to even get glassware that holds a decimeter cubed, they're big. So we tend to work in centimeters, and if you do, you have to convert the bottom number centimeters cubed. It's not a complication, not particularly complicated, it's just times it by 1,000. Okay, so then of course we end up with, so I'm going to highlight the one that comes up most often, which is really this one. But the V over 24,000, they'll actually give you the conversion, which is quite nice of them, and that seems to occur about 50% of the time, most of the time. So solutions, we then pick up a third equation, which is number of moles is C times V over 1,000. Now, those students who, again, have me will recognize that, and in fact, it's actually easier for me to say the students who don't have me, because those who don't have me might actually see that they don't get taught that, and they'll get taught a slightly different one. They just get number of moles is C times V. That's very common. That's actually the original equation. I'll explain why I don't like it in a moment. But you can also have MV as well. There's also moles equals MV, capital M as well. Now the reason for this is the capital M stands for the word molarity, which is the old name for concentration. By the way, it's not even an old name in reality. It's just, chemists still use this on a large scale, but concentration, you can use C in place of M to just use the word for concentration. And for me to give you guys this whole idea of molarity, which is exactly the same as concentration, by the way, it is identical to it. I don't like MV, but I see students using it, and it's fine too. But I'm not a big fan. So, but C times V, let me explain now the difference between these two. Because these are my two equations, and I'll box these both off, these two. And this one technically is the original, C times V. And the reason why it's the original is because we know that moles, of course, is measured in mole. And the concentration is always, and you guys all have recognized this, is moles per dm cubed. Now, there are other units of concentration, and hopefully your teacher has done this with you. For my class, you know I've gone through grams per centimeters cubed, grams per liter. But moles per dm cubed is the one that you're going to see most of the time. And what that means is, if you're doing moles per dm cubed as concentration, and you times it by a volume, then your volume would have to be in dm cubed as well. So this is the original equation, because the moles per dm cubed ties in with the same dm cubed in the volume. which will then give you the moles. By the way, if anybody's wondering, I'm going to just show you an alternative mathematical representation of this, which is moles. And I'm just going to put a sub in the units here, which is moles, with slash means divided by, even though you get taught the word per, which I don't like. That's moles over dm cubed, which I'm then timesing by a volume in dm cubed. And what you'll notice is the volumes cancel. This is why when you do C times V, you spit out moles, because the dm's will cancel. It's quite a nice thing. I put a rigid. Oh, I did, didn't I? There you are. Thank you, Ken. Oh, rigid. That's funny. Or regal, nice one. So it's just nice to understand what's happening in terms of the units. I always think it's lovely when it took me a long time as a student. I never understood how the units corresponded to the equations. So I try to incorporate it into my lessons, but it doesn't always work successfully, and it's tricky. So let me explain my change. So I now use C times V over 1,000, and this is because we always get given moles per dm cubed as a unit of concentration. However, we don't work in meters, in decimeters cubed. As chemists, we work on the centimeter cubed scale. We use it 90% of the time, 99% of the time, because we never deal on the liter scale. The only person who I know uses C times V directly is my technician, because I ask him to make me up, can I have 5 liters of hydrochloric acid, please, at 0.1 moles per dm cubed? And he'll be like, no problem at all. And he works in the liter scale. But he's the only person who does so. Everyone else in chemistry works on a tiny scale. So, and I'm going to show you how this links into the exam questions later. I have no idea, by the way, what I've just done with my bar there, but there you go. Okay, so the 3 moles calculations, I'm going to actually not bother to go through examples of this. I'm just going to bring it back to the exam paper momentarily. Okay, next one, of course, is empirical formula. So empirical formulae, and again, I'll take that one off. I'll tick off that one, although I want my green back, like continuity. Here you go. So I've just gone through the 3 equations, and you need to learn these, folks. Those are super important. All of those on that sheet right there is really important that you put into your memory, and it needs to be secure. Grams over grams, V over 24, C times V over 1,000. It's that repetition of saying them, and then practicing reorganizing them, really, really good use of your time. Okay, so we're up to type number 6, empirical formula. So empirical formulae is the idea that you can have different versions of this of a formulae, and there are actually loads of formula types. We've got molecular formula, empirical formula, we've got displayed formula, we've got skeletal formula. There are dozens of these, and the one that you come across here is something like, if I do, change my pen. So the example of empirical formula, I'll make my pen a bit faster now. So if I do empirical example, e.g., and put that in a box, because I haven't spaced this out particularly well, have I? Yeah. So empirical formula is this idea that you can have, now there's a couple of types of questions, and the first one would be C4H8. Now, I'd love to think year 10. Now, I haven't taught you organic yet, it's coming at you next year, but I'd love to think that you guys would have been picking up bits and pieces of this along the way, coming along to some of my additional lessons or watching some of my videos. But that's butene, or at least that's what we think it is from the initial formula. So that can be simplified. We know that I can simplify this. This could be simplified down to CH2. And this is just a mathematical trick. This is just simply realizing that, oh, we know that the subscript numbers of those 2 numbers can be divided by 4 as a total. And I can simplify them all down to the simplest. This is now, and it provides you actually the definition. This is the simplest whole number ratio. And now, simplest whole number ratio of atoms. Simplest whole number ratio of atoms of each element in a compound. Each element in a compound. Now, I know the definitions are horrible, and I'm happy at some point to sit down with some of you guys and come up with a list of all the definitions that are useful to know, and that is one of them. Simplest whole number ratio of atoms of each element in the compound. So what I've done is I've divided both of these by 4. I've just simplified it as far as I can go. I can't go any further because the carbon would be less than 1. So that's a very simple trick, but you then realize, people often say, what's the purpose of this? Well, this is something that's often skipped by chemistry teachers, and I think it's important to actually cover it, because I think most of the time, if students don't understand why they're doing something, it makes it inherently difficult, more difficult in order to hold on to that information. And the reason being is that our machines actually create the data. If I take an unknown compound of X and I put it into a mass spectrometer, a mass spec device, mass spec, what this will do is it will smash it into, it'll give us a series of data, including the elements that it was made for. So this was made from carbon and hydrogen, and it will tell us the percentage of each of them in it. So this will give, okay, 12 times. I'm having to do the maths then, of course, on my calculator in order to get it right. Okay, and then I do. So I've got 85.7% carbon, and therefore the rest would be hydrogen. Now that's a very common GCSE question right there, and they'll say give the empirical formulae. So the first step in the calculation, of course, is simply to work out the difference in of 100%, to work out the percentage of hydrogen. So 100 minus 85.7, or spit out 14.3%. Then what they'll do is you need that. Now that's what it'll also give us one other thing as well. It gives us the total MR of the compound. So 12 times 4 plus 8, 56. So it'll give us the total MR as well. And by the way, MR is collected in this case because, of course, it's covalent. RFM if it had been ionic, but RMM for this case. So 56. So I can now take this data and I can work out what the numbers are in it. So the first thing to realize is that we've just covered in this webinar that moles has a function, and its function is to count particles. Well, if I've got an unknown substance, but I know what particles are into it, I want to count them. So as a chemist, if we want to count particles, we need to get to moles. And if we want moles, well, we need some data that will allow us access to one of our three equations. So in this case, I'm going to convert them to grams. So if I just convert that percentage to grams, now I can do this because it's within 100%, and 100% of the compound, if I just treat it as 100 grams, those percentages that are in it will just translate to grams as well. So if I now, how do I convert something to moles? Well, I've got mass here, so this is grams over grams. What's the atomic mass of carbon is 12. The atomic mass of hydrogen is 1, so that's going to spit out a 14.3. And then 85.7 divided by 12. It's going to get divided by 85.7. My calculator is not doing very well today. Divided by 85.7 divided by 12 gives me 7.14. Right, I'm going to divide them all now. Now the thing is, though, I want the ratio. I want the simplest ratio, because what that now gives us is this is giving us the ratio in terms of the particle count. So I could technically write down C7.14 and H14.3. That is a formula, but the problem is it's not the simplest. And what I want is, it's also not a whole number. Well, what I can now do, of course, is I can simplify this down. I can divide them all by the smallest one. Now, what that will inherently do is it will, of course, make one of them become the number 1. And in this case, it's carbon. So if I do 14.3 divided by 7.14, I get an exact number of 2.00, which is 2. So I get my final formula of CH2. There's my empirical. And I can do that purely from percentage data given to me by my mass spec device. Now, I can then translate that into a real one by understanding that if this is the simplest version of it, and this is the actual MR, this is how much it really weighs. And in that case, I can work out how much they've divided it by. We recognized in this step, what we did here was we divided this by 4. And we did that because the C was the lowest number. Well, I can work out the same for this one. What did I divide it by? Well, how much does the empirical formula weigh? Which is 12 plus 1 times 2. It's nice to do that in good chemistry, which is 14. If I now divide 56 by that fraction, by that part, that simplified version of the molecule, 56 divided by 14, I get an exact number of 4. So they divided it by 4. So I'll just times all of these numbers up, once again, by 4. So it's just nice. It's all coming from a machine. This calculation wasn't really so much created, so much was an output of the machines that we were creating to be able to analyze samples of unknown compounds, which I kind of think is an amazing bit of science, really, that the maths came from what we were creating. It's kind of nice. So we've got empirical formula covered. And remember, it all came down to counting particles. All I simply said was a mass spec device tells me what particles are in something. and it can give us the percentages. Well, I can count those I can turn those percentages into grams, and I can count them by turning them into moles. Once I've counted the number of particles of each one of them, I can simplify them down to the lowest form simply by dividing it by the smallest. Quite nice. And it's also, I tend to teach this in a rhyme: percent to mass, mass to moles, divided by the smallest, I find the ratio. It's quite a nice way of doing it. It's relatively simple and easy to remember. Kind of rolls off the tongue, although people have argued with me over that. Hey, Emmeline, thanks for coming. Right, okay. This is probably the one that everyone dreads the most. This is reacting mass calculations. Now, reacting mass calculations are the ones that most students dread. All of these, by the way, are relatively high-level questions, but as you'll probably realize, as we move down the list, I'm actually increasing in level, in difficulty-wise. If you'd like me to level them, I won't do this precisely, and teachers probably wouldn't like me for doing this, but I like to think that the AMR would be, this would be kind of a level 4-ish. I'm going to make my pen a little bit thicker for that, make it easier to see. So I'd probably say that AMR is a level 4 at GCSE. 4 million equations is definitely a step up, so that's going up to like a level 5. Percentage composition then drops. These two, by the way, both on a level 5, although I'd probably say that equations vary massively, and you'll see that in a second when I go into the exam paper. So the percentage composition is back to a level 4. Moles calculations, of course, now that we've got to select which mole calculation and usually extract it from the data, you're jumping up to kind of a level 6, 5, 6-ish. Then empirical formula, again, probably level 5/6. Then you get into reacting mass, and we're into 7/8 here. Now, they can make these much harder, but that's usually the level that we're at. Percentage yield is low, usually at level 4/5. I'll put 4/5. Excess reagent calculations are 8 to 9, and water crystallizations are usually a 7 or 8. So they do vary, though, and in fact, the paper, the questions I gave you were from the relatively recent ones that I sent out as the work booklet for you guys to do the actual test. They were actually very challenging questions, and the reacting mass one I seem to recall being quite a high level 8, level 9. But we'll have a look at that in a bit. So, reacting mass calculations. So, reacting mass calculations, this is type number 7. So this is simply recognizing that in chemistry, we can predict things. And we realized, I'll drop over onto this side if I can. See if I can find some space. So, reacting mass calculations. So this is the idea that we can predict using chemistry. If I take, and I'll do the one that all my students in class will recognize. If I take hydrogen gas and oxygen gas, I'm going to create water. This is what NASA do on a regular basis when they want to send stuff into space. Take hydrogen gas, which is explosive, they add it to pure oxygen, rocket, and the hydrogen, of course, is the rocket fuel. The oxygen is the oxidizing agent, and you form water, and it gives out enormous amounts of energy. So first thing, once I've created the equation with the correct formulae, H2O2 being the correct formula, these are commonly missed. Do watch out for these, please. Know your diatomics. Anything that ends in ene or gen is diatomic. And then, of course, students forget to balance. Now, what students don't realize is that balancing an equation like that is they don't really understand why they're doing it. They get told by teachers that it's to do with conservation of mass, and it's a very good rule. They'd say, the particles that go in must come out. I totally understand that. It's not really the real reason. That's just common sense. The reason why we're balancing an equation is it provides us a ratio between the molecules that are being used or produced in the equation. And what this says here is that 2 molecules of oxygen, 2 molecules of hydrogen are reacting with 1. There's an invisible 1 here. Remember, I'm going to balance my equation in red, and I'm going to do something which some students don't like. I think it is important really there to show the 1, the invisible 1. And what this is saying is that 2 molecules of hydrogen is reacting with 1 molecule of oxygen. 1 molecule of oxygen, and it's forming 2 molecules of water. Now, what it's really lovely to do now is 2 molecules of water. So, what it's really nice to do here is just to bring your attention to the word mole. The word mole, everyone thinks is a stupid word within chemistry, and they ask why did they call the chemistry unit for counting particles a mole? And I said, well, it comes from the word molecule. They just wanted to shortcut it because they were using the word molecules in written sentences for a long time, and it just kind of happened. So we've got 2 molecules reacting with 1 molecule, creating 2 molecules. Well, what we now need to do is just realize that we can count particles. So if I'm given 25 grams, I'm going to keep it really easy. I'm going to do 8 grams of hydrogen gas. Well, grams to a chemist is no use, really. Grams is not allowing us to count particles. What we need to do is we need to get to moles so we can use the equation. So what I do, the first thing is to realize that I'm in grams over rams again. So this makes it very easy. So grams, I've got 8 grams of hydrogen. So how much does hydrogen weigh? Now at this point, students tend to put something in which they shouldn't do, which is the big number 2, and you really shouldn't do that. Because how much does hydrogen weigh? We're trying to count hydrogen. Hydrogen weighs 2. Has nothing to do with the fact that there's 2 of them. Hydrogen always weighs 2. So if I do 8 over 2, I've got 4 moles of hydrogen gas being given to me. Right, now how much oxygen, how much water, how much oxygen am I going to need to react with it, and how much water am I going to make? Well, according to the equation says it provides me with what is called a mole ratio. And this is one of the most important and fundamental pieces of chemistry. And it's really poorly taught. It's not emphasized enough. It's something which teachers just, because as chemistry teachers, A, we like to show off, and B, it's very easy for us to forget what it was like to not realize that this was such an important part of chemistry. And so it just tends to be just kind of assumed this understanding is seen. But anyway, the ratio says 2 to 1 to 2. So if I was given 2 molecules and I'd need 1 oxygen, well, to get from 2 to 1, the ratio of those 2, I need half as much. So I'd divide it by 2 if I wanted to get from the 2 to the 1. So I had 4. So I'm going to divide that by 2, which gives me 2 moles of oxygen. And then if I want to go, oh look, 2 to 2, it's the same number. So 4 moles of hydrogen will give me 4 moles of water. All I've done is used the ratio from the equation. That's why we balance, because it allows us to translate across substances through the equations. And that's an awesome thing to understand. It's really incredible once you actually realize that people were realizing this before it was even understood that particles were even existing. It's a fascinating thing. So we've got 4 moles going to 2. So what that means is if I've got 2 moles of oxygen, well, the problem is you can't go into your exam and say, oh, I've got 2 moles of it. So we need to convert that back to grams again. So what we'll do is we'll just take our original equation, grams over rams. Now at this point, my students will realize how I like you to do this properly. Do the original equation, don't use your triangle. Rearrange it, times both sides by rams. All we're trying to make is grams the subject of the formula. So the rams moves over here, and that cancels out. So grams equals moles times rams. So if all I need to do is know how heavy oxygen is. And oxygen is 16 on the periodic table, it's traveling around in a pair. It weighs 32. So if I do 32 times 2, I get, let's just, don't worry, I'll erase it. I'm going to get 64 grams. That's a different way to say. 64 grams of oxygen. Now the great thing, and I love this bit, because if I take 8 and 64, those are what went in, these are the reactants. And it's always nice to remember that conservation of mass, which I mentioned earlier, and to realize that mass is conserved. So if I do 64 plus 8, I'm going to get 72. So I've got 72 grams of water. Well, we can just check this with our moles, because we said that there were 4 moles of water produced. Well, how much does water weigh? Water is 1 times 2 plus 16. So that's going to be 18. So 4 times 18, again. 18 times 4. Tell me, I'm sorry I'm doing that, is 72. So it's nice to see that the conservation of mass is a true thing, but also that the chemistry, the use of moles was also correct. This is how they knew what they were doing was correct. It was following that what they were making was what they were expecting. It's really lovely to understand the chemistry and where it's coming from. So reacting mass bonds, this looks awfully complicated. It really isn't. I'm doing a very simple set of steps, which is I've been given grams. I'm converting it to moles. So I'm doing grams to moles. And then I'm multiplying or dividing by the ratio. So if we put that into steps, we're going from mass to moles. Then we're doing multiply by ratio. I prefer use ratio really, but I'll put use ratio, step number 1, step number 2. Use ratio from equation. Use ratio, that'll give you the new moles of whoever you want. And the third one is moles to mass. It's really not that complicated. Those are the 3 steps I'm doing. I'm just listing it all down and showing it in its entirety. But it's a very straightforward thing, and students get very freaked out by it. I think when they first hear it, it's quite alien. And I do understand that, but it's not something that actually is too difficult. So anyway, let's move on. let's go on to I can now tick off reacting mass. Percentage yield. Percentage yield, very straightforward. You've just realized, and by the way, I hope you realize that there is an order to this. I don't know why, by the way, the keyboard keeps popping up. I have no idea. Percentage yield. So we've just calculated that we're going to make, in terms of water, we're going to make 72 grams of water if we burn 8 grams of hydrogen gas and 64 grams of oxygen. Now, in reality, I don't get that. I'll get something close to it if I do it well. But the problem is things get lost, things escape, incomplete reactions, side reactions, all those reasons. And what we're going to say is that I didn't make 72 grams, I made 68 grams. And what's my percentage yield? See, it's very, very straightforward. So percentage yield is what you got over what you were expecting. And what you'll realize is times 100, and it always gives you less than 100%. So if I did 68 grams, I was expecting 72. I got 94. 94.4%. Great yield, good yield. But it's a very straightforward calculation. Don't want to waste your time with it. You know, I've done 40 minutes on this already. Next, excess reagents. This is a tricky one, realizing that this is what we got given in the question. You realize that everything is kind of, these last few are exploring the understanding of this whole reacting mass calculation. Because what might have happened, instead of being given 64 grams of oxygen, I'm actually given 120. And if I was given 120 grams instead, what I need to realize is that what I've been given is too much. This is called an excess reagent. And what you always do is you always ignore the excess reagents. It means you're not going to use it all. It's going to be stuff left over. So all you simply do is ignore the excess reagent and use the other one to work on your mole ratio within your equation. That one will become easier to understand when we look at questions. Last one, of course, water crystallization. Still don't know why my keyboard's popping up. Done it again. Don't know why. So my water crystallization is, I'm going to explore these two further, and you know, I'm not going to go through them. I'm going to drop straight into. I just want to quickly run through an exam paper with you guys that I've set up. So I went on to physics and maths tutor because I've really, in lessons, it's very difficult for me to find the time always to look at exam questions and do that bit. I'm busy teaching content, and I don't get enough time really to explore papers as much as I would like until we get into the real revision at the end of the year. But this is a nice opportunity for me to actually show you how this webinar today links in. So this is January 2017 from the IGCSE Ed Excel, and I've gone through it really quickly just to, and by the way, this is the paper one, so this applies to all students who are doing dual science or triple science. And it's nice for us to spot all the questions that relate to my webinar today. So the first one was just simply choose the correct symbol for an element. And realizing that we've got compounds here and here. This is not a compound, this is a molecule. It is an element though. An element. That's clever, isn't it? Because that's, the question says there, it's a trick, isn't that nice? Symbol. So it is symbol for an element. This is a molecular formula. That's a molecule, not a symbol. Symbols come directly from the periodic table. So we had to realize that that one, of course, it is an element, but it's not a symbol, it's a formula. We've got water, compound, hydrogen peroxide, compound, symbol of an element is here. So it's just bringing us back to recognizing the periodic table and where the symbols are. So it's really part of formula. If I now scroll down to the next green circle patch, and there we go. So the next one is they've gone into an equation. So notice what they've done. They haven't done relative, they've skipped AR and MR, my first type of calc, and they dropped into initially formulae, which it was a very interesting question and a very easy one to be trapped by. They then dropped you into one showing, oh look, can you produce a product? So we've given you the two inputs going in, and they've given you the word equation. What they're now saying is, can you convert this into a formula? And it's quite a tricky one, of course, because it has a complex ion. The ammonium is NH4+. The only positive complex ion that you guys need to know, and of course the chloride ion is Cl-. So they cancel themselves out, so you can do the cross and down trick if you like. What was it, drop and swap? Well, like that. So that's a 1 there, that's a 1 there, so it's just cross them down. But in reality, the charge is cancelled, so it's ammonium chloride. And what you'll realize is that the product, there is just one and the equation balances, which is nice. It's kind of a confirmation that your formula is correct. If you put in the wrong formula and the equation doesn't balance, then you're wrong, which means you can't change it. There isn't ... here for you to change this. It's quite nice to do that, swap and drop. Thank you. Yeah. So there's ammonium. So there was a perfect example of how they're doing, how they were testing this. They were testing your ability to create formulae and then linking it to equations to put it into a slightly harder context. So it's quite nice to see that. Next, state symbols. Nice to see state symbols appearing. Let's go down until we see the next one. There's the next green bit. There we go. So the next one is balancing. Again, part of my equations. And I haven't actually done the balancing part of the webinar. And really, I could do an entire webinar just on balancing. It's called stoichiometry, by the way, the study of balancing equations. And this is just, can you balance? Let's run this one just for fun and games. One carbon, we're good. 4 hydrogens, oh, got 2, can double it. 4, right, I've changed somebody, start again. 1 carbon, 4 hydrogens, oxygens, 2, how many have I got over here? 2 and 2, 4 in total, I'm done, first equation finished. Let's do the next one. 2 carbons gone in, 2 carbons come out, sorry, 2 carbons come out now. Next, I've changed somebody, start again. 2 carbons gone in, 2 carbons gone out. 4 hydrogens in, 4 hydrogens out. I've doubled it. 2 out, and I've doubled it. So there's now to 4. I've changed somebody, start again. 2 carbons, 4 hydrogens, oxygens, 2, 2, 2. So I've got 4 oxygens again. Isn't that fascinating? So I've got 4 again, so it's the same. There we go. A nice simple balance equation, but again, part of the test. So they've covered so far formulae, equations. Let's see what they then managed to do in this paper. Looking for the next green one. There's relative atomic mass calculation. Next, there's my next green bit. Oh, a far harder equation. Now they're really getting into this. What a step up in level that is. Because first of all, they're saying, do you know what the products are? And there were lots of students who won't. So lithium into water. I'd love to put it out to the classroom. There's only 3 people watching, although I don't think that number is correct, but not that it matters. Would anybody in the chat room like to tell me what my products are going to be for this? Lithium plus water. Big delay on the chat. So we have lithium hydroxide, hence why they're called the alkali metals. LiOH, that's correct. So we've got lithium and hydrogen, now we need to balance it. Now they've already balanced part of it for us, which is quite nice, because it means that I'm guaranteed my numbers, 2 lithiums and 2 lithiums. Right, hydrogens are 4. Oh, that's a clever trick, isn't it? How many students are going to go, oh yeah? No, don't forget, you must always count everybody. I've got 2 hydrogens here and 2 hydrogens here. It's now balanced at that point. Clever trick, like it. But far harder, looking for you to know, now that is recalling real knowledge now. You've got to there, I put caps so it's more accurate. I like it. Yeah, totally true, I agree. Next, okay, so we've just gone into a far harder formulae. I mean, how many people are just going to forget the diatomic alone, let alone remembering the formula for lithium hydroxide? Not easy, that. And having to remember the products anyway, tricky. Right, and then big step up. So at this point, we now drop into our moles. So we've got silver can be obtained from silver oxide. 32.4 grams of silver is obtained from complete decomposition of 34.8 grams of silver oxide. Calculate the mass of oxygen formed in this decomposition. Right, so this is a relatively easy one because it's a mass defect. We've got silver oxide going to silver and oxygen. Right, well, this is simply a mass difference. They've given us the mass of this. This was 34.8, and this is 32.4. So whatever is left is oxygen. So just take away the smaller from the bigger. Relatively easy. Determine the empirical formula. And you're going to need moles. Right. So now we drop into our empirical formulae, which is you're doing your silver. Okay, I'll put in your elements. Silver now. Right, we need to get moles. They've given us, how much silver was there? 32.4 grams of silver. How much oxygen was there? Not a lot. Very, very small amount. 34 point, I should be able to do that in my head. 34 minus 32.4. 2.4 grams. I'm an idiot. Right, and that's actually giving us grams. Right, to convert to moles over silver. Ooh, silver's heavy. Silver is very heavy. I should know this. 10 something. Silver, Ag, here we go. 107 or 108, I think, on your table, most likely. 108. So that's divided by 108, and that's divided by 16. 32.4 divided by 108 gives me 0.302. 303 actually, if I round up to 368, probably. 2.4 divided by 16 gives me 0.5. Divide them all by the simplest. 0.5, 2. Yeah, that's correct. So there's our improvement. That's a very interesting thing now. It's a lovely thing actually, because it's nice to remember that silver is always +1. This falls into the ballpark of that. Okay, let's go back down. Let's see if we can follow through and look at another one. This time completing word equations. So this is knowing your products and understanding how reactions behave. Magnesium and sulfuric acid, magnesium sulfate and hydrogen gas, metal plus acid, salt and hydrogen, match. Copper oxide plus hydrogen. Oh, that's clever. It's going to form water and copper. The hydrogen's going to steal the oxygen. That's tricky. Swap, if you're ever not sure, swap the female, swap the oxide. So it's going to be hydrogen oxide and copper. Next one, anhydrous copper sulfate and, ooh, that's interesting. They've given us nothing there. Wow, complete the word equation. Is there something that I'm missing from the question? Very likely. Anhydrous copper sulfate plus water from the picture. That's neat. Clever. Plus water goes to hydrated copper sulfate. I would leave it blank. Yeah. Okay, next, nice then to say, next calculation, suggest the formula of the salt formed. That one was fascinating. Never seen them do this before. It's a really unusual sulfate. It's actually a different sulfate than what you're usually being asked for. So this is magnesium oxide plus SO2. Now, if you add those two together, what you make is magnesium sulfate, but it's an unusual one, MgSO3. They add together. Now that's a rare sulfate. It's actually called magnesium sulfate 4 is what that is. Sulfur's in an oxidation state of +4 rather than +6. That is a level 9 at GCSE. The reason being is everyone is going to put MgSO4 because that's what they recognize. But that won't produce MgSO4. It just won't do it. There's no way you can put them together to make that. You're going for magnesium sulfite or magnesium sulfate 4 from new name. I just gave you the common name of the sulfite. Next, again, into moles calculations, but this time, look, oh, we've got grams appearing again, but then we've got concentration and the volume. Amount of copper oxide, there's grams over rounds. There's grams over rounds. Moles of sulfuric acid, there's moles equals C times V over 1,000. Why is it over 1,000? Because I'm in centimeters cubed in the volume. So it's nice to see both moles equations appearing, and then there's my water crystallization. So you can see they're giving you an awful lot. Let's see if there's any others. I think there is actually. I think there was another one. Yeah, there you go. There's an empirical formula and a molecular formula. Clever, you have to do both. It's giving you the ratio. That's an empirical. So empirical, it's nice. So now I don't want to get, I'm getting completely lost in this. I've done nearly an hour already, but what I want to just quickly flag up is how many of these questions, the AR and MR, you've got to add it to your calculation. That was there. I don't like scribbling like that. That was in your exam paper. Formula was, equations were. Percentage composition didn't appear. Moles in solids did. Moles in gas solutions did. Empirical formula did. Reacting mass did. Water crystallization did. The only ones that didn't appear were percentage yields and excess reagents. It's a lot. You realize how these calculations permeate your entire exam. So it's an important thing for me to go through with you. Okay, so I've had like a brief look, and I'm going to, I still haven't forgotten that I haven't ticked off the excess reagent and the water crystallization. I'll come back to that. Now what I want to do is I want to quickly go through this exam paper that I set you. So I set you a 52-mark exam. It was just a practice Calcs paper. I did it in 36 minutes and 9 seconds. And I got 51 out of 52 marks. Yes, folks, that's correct. I lost 1 mark, you'll see where. But it was a good thing for me to actually have done. So I went through it, and the first thing I think, you guys have all marked your papers, of course, and it's really me talking through it. First thing, I love the reminder of bonding. That just makes me I don't think anyone really wanted to see that, but it was. So we've got a compound, of course, of ammonium, it being covalent. I've given you the formula next door. Simple covalent as well, not that it's needed. Hydrochloric acid, hydrogen chloride is a compound, covalent again, HCl. Oxygen, we all know this is an element, but it is covalent, found in a pair. Magnesium oxide is a compound, it's ionic. Okay. Next, of course, we asked you in this calculus just simply to give the right formula. So I did the whole thing. I did the cost of your swap and drop, X factor, and then simplified the numbers down to the MGO. I don't actually like doing the X factor. I like the cancellation of charge better. It's recognizing that the compound has an overall charge of 0. So if I had aluminium plus 3, chloride 1 minus, I'm going to need 3 chlorides to cancel out, because that's 1 minus. Well, I'm going to need, if I times that by 3, I get minus 3. That minus 3 cancels out with plus 3, which gives me AlCl3, and that's then got no charge. So I prefer the cancellation of charge rather than swapping it up. I think it's a better understanding, and it's going to be important because you're going to see that later on. Next thing, which state symbol represents the physical state of hydrogen chloride at room temperature? This one comes up a lot, definitely one that I would emphasize. Hydrogen chloride is a gas. Now, this is a trap, and everyone in this room would go, hey, Chris, and I totally get it. Or even liquid. Those are the two that are going to come up, because you see hydrochloric acid in a bottle. You never see it as gas, but actually, hydrogen chloride is a gas, and it's an invisible gas. And the reason being, of course, is because it has winds between the molecules. It's simple covalent molecules, and it has winds between them. And those weak intermolecular forces are very weak, which means it's a gas. Let's do the explanation. Next, so this calculation's now started to appear. All right. Now the calculations. So they gave you, first of all, this. Can I just say, guys, for GCSE, this was tough. One of the hardest sets of questions that I've seen in a while, and these are the latest ones. So be aware of that. So balancing an equation, I think most students would be okay with this. Then also, we're asked to transcribe a formula into a name. 2 substances that would be solids at room temperature. Right. At one point in the temperature, right, so we get to see, they've given us a temperature, given us that, and they've given us the melting points. And what we realize is the only people who are going to be solids are the ones that are above. So, plot them down, they've given performance. Suggest the most likely type of bonding in neodymium fluoride, metal, non-metal. Going to be ionic. Very reasonable. Right. This one was the first, this is a level 8. It's nice to level all of these. But this is level 8/9. And it was a really clever trick. And for 1 mark, I thought that was fascinating. They pushed you really hard for 1. And that kind of makes sense. Most students would be kind of a little bit lost in this. They ask you for the formula of neodymium oxide. And what students are going to do is they're going to go to my beautiful table. They're going to go for my gorgeous, gorgeous, gorgeous table. And they're going to find that neodymium, which is here, by the way, neodymium will not be on your table at GCSE. Let me show you why. Because at GCSE, you are given, this is your GCSE periodic table, folks. And look what's missing. The answer is the block at the bottom. This orange and brown section at the bottom, these are the lanthanides and actinides. And this is the lanthanides at the top, actinides at the bottom. And that section isn't even on your periodic table. What that means is, when this question appeared in the GCSE, students go, that's not even there. So how do I know it's charged? You know it's charged because they've already given you a formula. That is really, really tough. You had to dismantle neodymium fluoride. So you needed to realize that F was 1 minus, and that neodymium is a question mark. You need to say that they needed 3 of them. So times that by 3 gives me 3 minus, which means neodymium must have been 3 plus. That is one of the hardest formulae questions I have ever seen. Really tough because they didn't allow you to use the periodic table. Once you've dismantled neodymium fluoride, you get the charge of the neodymium. Then, of course, you can find the charge on the oxide in the periodic table. It's -2 because it's in group number 6 over here. This is the -2, so we got +1, group 1, +1, group 2, +2. Skip these because they're transition metals, they have multiple charges. +3, -4, +4 can be both or nothing because it's covalent. So +1, +2, +3, nothing, -3, -2, -1, nothing. So that, by the way, if you weren't sure what I just did there, please come and ask me at a later date. But I get my oxide as a -2. Right, ups and down. It's a useful trick. Swap and drop. And I get neodymium oxide as ND2O3. Hard question. If you got that, well done. Next, dropped into bonding again. I apologize. 4-mark question. They asked you to do malleability and conductivity. So malleability is due to the atoms being in layers, and the layers can slide easily past each other. Conductivity is due to it having a sea of delocalized electrons that can flow through the structure to carry the charge. Right, into calculations. So they gave you a rather mean, in my opinion. They gave you a rather mean set of equations. They gave you a 3-step reaction. It's very by the way, this is actually very uncommon at GCSE, but very common at A-level. But they're really starting to really amp up. That this level 9 has meant that there has clearly been a big shift in the level of the calculations that are being asked for. So first of all, write a chemical equation for the formation of sulfuric acid from oleum. Now that's really hard, because what you have to do is you have to read through it. You have to identify oleum for a start. There's oleum. Then you have to realize I need to turn oleum into sulfuric acid, which is here. Now I know that one. And then what we need, but then luckily it did tell you in step 4 that they added water, and then you had balance. That was hard. That for 1 mark. That's again a level 8/9. Really tough, folks. Giving you a substance like oleum, that's otherwise commonly known as fuming sulfuric acid. That's hard. Very, very. It's a spook question. Next. Sorry, I'm having hot coffee. A mass of 80 tons of sulfur is reacted in stage number 1. Calculate the mass in tons of sulfur trioxide made that can be produced in stage number 2. Right, stage number 2. Look what I've now done. Now they gave us the conversion. Times 10 to the 6. So I did 80 tons of sulfur reacted in stage 1. So the first thing I did was I need 80 tons in moles. For me to use an equation, I need moles. So how do I get to moles? Grams over rams. So the first thing is they've given us the conversion. There's the conversion, folks. Giving you it. So 80 times 10 to the 6 over 32, which is the mass of sulfur, and I get 2.5 million moles. That's impressive. Next, what is the ratio? So once I've got 2.5 million moles, I can now go, right, let's look at my equation. What's the ratio? Well, if I use sulfur, I had I'm going to zoom right in on this as much as I can. Yeah. I have 2.5 million moles of sulfur. The ratio from here to here is 1:1, which means I've got 2.5 million moles of sulfur dioxide. That 2.5 million moles of sulfur dioxide goes into here. All right, so I've got 2.5 million moles of sulfur dioxide, and that's going to go to sulfur trioxide. And the ratio is 1:1, which means I've got 2.5 million moles of sulfur trioxide. So the ratio is 1:1. So what that now means is I've got the moles of it. Just need to multiply it by its MR. And they told us that did they give us that? No, they didn't. So SO3, what does sulfur trioxide weigh? 32 plus 16 times 3. You realize that AR and MR just permeates all the way through all of your calculations. And it's 80. So that weighs 80. Has a relative molecular mass of 80. And so reorganize my equation. And so 2.5 million multiplied by 80 gives me 200 million grams of sulfur trioxide. Converted that into tons. Getting my answer. Hard. Guys, this is GCSE level now. That's tough. Realizing that they're giving you industrial sizes, industrial quantities. This is something I haven't done enough of in lesson. I have done it a little bit, but not enough. Next, calculate the volume, the minimum volume at RTP. By the way, RTP stands for room temperature and pressure, which is 25 degrees Celsius and 1 atmosphere. Or 100 kilopascals. So, not that it matters, it means that you can use V over 24, because right. They wanted in decimeters, so number of moles is V over 24. They've given us that. Next, but the problem is, we were working in grams originally. Calculate the minimum volume of cubic decimeters of oxygen to react with 64 tons of sulfur dioxide. Right, that's tricky, because the first thing I've got to do, I've got to do 64 tons into moles. So, grams over grams. I'm going to do the same conversion again, over 64. Oh. I've done this somewhere. Hang on, I've done it all here. Right, folks. Problem is I've separated it all out and I've not then used it particularly wisely because it's out of order. I don't really like that. So okay, grams over grams. Look, there's my conversion. There's 64 tons, folks. So it's okay. We can work through this. We've got grams over grams in my equation, and I have converted the 64 tons. Then I've worked out the MR of sulfur dioxide, because that's what that is. So the sulfur dioxide weighs 64. What number does that spit out? That spits out this number here, 1 million moles of SO2. Now the SO2, the ratio with oxygen, where's the equation? The ratio with oxygen and sulfur dioxide is 1 to 1/2. So by the way, notice my routine. I first of all got to moles. Then I'm looking for my ratio. And then use the ratio, divide it by 2. 5 million moles of oxygen. Now I use V over 24. I've got the moles. I've got 24. Reorganize. 500,000 times by 24. My answer. This is not easy, folks, and this is GCSE. So definitely worthwhile going through this. I'm happy if you want me to give you another paper, and I'll do another webinar before the end of the summer. Happy to. Next question is on water crystallization. So they've taken a sulfate crystal that has an unknown amount of water. Right? They heat the mass of the tube empty. The mass of it plus the hydrated salt. Mass of tube after heating. Right, calculate the mass of the sulfate formed after heating. Well, that's the mass after heating. That's the mass of the tube. Minus them away. Relatively straightforward. Just using data. Next, calculate the mass of water collected then. Oh, okay, well, hang on a minute. We've just worked out the mass after heating. Well, we don't know the mass before heating, so we had to do that first. So we had to work out the mass before heat. So this was the mass of the tube and the hydrated salt minus the boiling tube gives us 8.61 grams of the hydrated salt. So that there is that guy. Next, well, hang on a minute, because this one is just the sulfate. So I have to minus that away to get the water, hence 3.78 grams. Next, the relative formula mass of zinc sulfate was this. Calculate the value of X. Right. So this is this water crystallization. Now the reason why I do this last is because water crystallization requires you to have all of the calculations at hand and be able to do it. So we have a zinc sulfate, and it was bound to an unknown amount of water. Now I hope you would all agree with me is if I say zinc sulfate, I have got one of them. There was an invisible number 1 in front of it. And what I want to know is the number of waters. What I need to do is count particles. And if I want to count particles, I want moles. I want to count how many waters there are compared to how many zinc sulfates there are. So let's count them. Well, we just worked out in the previous questions that the zinc sulfate was 4.83 grams. That was just that big. And the water was 3.78 grams. Just the water. Well, grams is no use to me. I need moles. So they told us that that was 161 on its MR. And everyone knows that the water's MR is 80. So 4.83 divided by 161. I mean 0.03. 3.78 divided by 18. I mean 0.21. Divide them all by the smallest, which gives me 1 zinc sulfate. It links to there. How many waters do I have over 0.3? 0.21 over 0.3, and I get 7. Oh, I just didn't know. 0.21 divided by 0.3 gives me 7. So I have got X. So it's, I hope what you all realized here is this is a form of empirical formula. It comes back to that same process. Find the mass, find the moles, divide them by the smallest to find out what the ratio is of water to 1 zinc sulfate. Next, why is it necessary to heat the crystal constant mass to ensure all the water is left? Because otherwise, if you don't, then you're not going to end up with the correct value for X. It'll end up being smaller. You didn't lose as much water as you'd hoped to. Always heat in constant mass. Describe how the students could use a chemical test to show that the liquid was water. Love this. I had to add this one because it was this chemical test appears all the time and students forget it. It's because of the word anhydrous. So the word anhydrous means without water. So we're using anhydrous copper sulfate on a small amount of the liquid to it, and it will change from white to blue. Next, piece of apparatus, measuring cylinder. Reading off it, 44 centimeters cubed. Right, calculate the moles. Now in this case, the question was very straightforward. You've got the volume from here. Sorry, let's do that again. So I've got the volume from here. Here's my vol, here's my V, and there's my C. So, and don't forget, I am in centimeters cubed, which means it's my good old C times V. So, okay, that's straightforward. One mole is through. Got our concentration for the question, got our volume for the question, and we get to our moles of 4. It's easy, just to use the equations. Next, a student poured the solution containing 0.01 moles of hydrochloric acid into the beaker and then added 0.075 moles of sulfate. Hydrogen was collected. Is the zinc or hydrochloric acid in excess? Explain your answer. Right, this is the excess calculations, this excess reagent. This is understanding that in chemistry we never add the right amounts of anything. It's impossible to do so. You can't even weigh out 25 grams exactly. There's always going to be limits over, even if it's 0.00 whatever. So we always have something that there's more of. And the question that told us there is they've given us 2 moles values and said, do you understand what an excess is? Now, this was actually quite a nice question because what they've done is they've given you, these are the 2 moles numbers, 0.0075 from zinc and 0.01 of HCl. Now here's the problem, the ratio is 2 to 1. What that means is it's a little bit more tricky to work out who's in excess. Now what you want to do is just cover up one of them. Make one of them disappear. Right, now if I was given 0.01 moles, let's actually write that in, moles of HCl, how much zinc would I need? How much zinc would I need to use it all? And the answer is, it's a 2 to 1. And that is the amount of zinc I would have required. Half the amount. How much did I have? I had more than that. This number is bigger than this number. I shouldn't do that. This number is bigger than this number. This is therefore in excess. It's a clever trick and it requires a bit of practice. I'm happy to spend a bit more time doing that. But definitely one that needs talking through. And then I've just said zinc is in excess because there are more moles of zinc than is needed. The effect, it then says, student repeats the experiment with magnesium at the same total surface area. What effect would this change to the rate of reaction? The rate would increase due to magnesium being more reactive than zinc. I thought that was really cheeky. Throwing in a reaction, reactivity of methods question into a Calcs curve. What effect would it have on the volume of hydrogen? The answer is nothing at all. And the reason being is look at the 2 equations. 2 equations have the same ratios. If I use the same amount of moles, I'm going to get the same moles of hydrogen. I'm just going to make it more quickly. Remember that. All in the equation. Again, I don't spend enough time doing that in class, and I definitely need to do more of it. Question number 6. Right, again, they've given you 2 equations. How mean? Definitely some. This is a bit of repetition that I'm starting to see, and definitely need to focus on this in the lesson. Please ask me to go through a few in supervision sessions if you need them. So, explain with reference to the equations 2 advantages of using lithium peroxide rather than lithium hydroxide. So they're removing carbon dioxide in a spacecraft. I thought this was really lovely. So lithium hydroxide will react with CO2 that the astronauts are producing and convert it into solid lithium carbonate and water. Now the water would be useful because you can drink it. How good's that? Well, if we use lithium peroxide, it will react with the carbon dioxide and I will make hydrogen gas instead. So the first thing to note is, why would this be put? This was a common sense question. The lithium hydroxide, number 1, removes twice as much. The ratio is 2 to 1 here rather than 1 to 1. Sorry, it's 2 to 2 rather than a 2 to 1. This still removes twice as much. The first one is a 2 to 1, that's a 2 to 2. It removes twice as much CO2. And it also produces oxygen as a byproduct, which is very useful for these cases. Okay. We're nearly at the end now, folks. Don't worry, nearly at the end. Next, right into a proper calculation. Calculate the mass of lithium hydroxide needed to react with 100 grams of CO2. Right, well, the first thing I'm going to do is I need to work out moles. So, moles is grams over grams. There's my equation. Followed by 100 grams over 44, the relative molecular mass of CO2. I get moles of carbon dioxide. What's the ratio from the equation? It's 2 to 1. Right, multiply the moles up. So I divide the moles to give me carbon dioxide. But hang on a minute, which one have I just worked out? Oh, it's 100 grams of carbon dioxide. Notice my outline. Yeah, I've just worked out the moles of carbon dioxide. So I need to remember that the ratio is going in this direction. So I'm timesing by 2. Right, times that by 2, and I get a moles of. There we go. I get a moles of this guy. Times it by 24 at the end, because that is the weight of lithium hydroxide times by 24, and I get a mass of moles. That's tricky, but you see the process is the same. Get to moles, use the ratio, get out moles. Not complicated. Next, calculate the volume of carbon dioxide at room temperature and pressure removed by the 100 grams of lithium hydroxide. Right, same thing. First of all, grams over ounce, moles. Use the ratio, it's 2 to 2. So the same number of moles of CO2 will be removed. Right, assume that 1 mole of gas has a volume of 24,000 centimeters cubed. Right, reorganize the equation. So that was going to give me my V. So times 2.17 by 24,000. And I get 52,174 centimeters. Next. Right. Why does the mass decrease during heating? Carbon dioxide is lost as a gas. Are we decomposing in carbonate? Yes, we are. Sometimes it's water as a gas. This is where I lost my mark, folks. So state the color of the solids in the reaction. I put green-blue. It's turquoise. Copper carbonate is turquoise. And on the mark scheme, it says except green. So there's my 1 mark, folks. It wasn't a calculation, it was a color. So they want green now. It's turquoise, it's greeny blue. I totally disagree with it, but whatever. It's green. I'll give it a So copper oxide, of course, is black. Which experiment might not have the heat? Which one did not? 26 is decreasing. It's still decreasing. It hasn't finished. Number 1 was definitely not. Which statement could explain how the decomposition might not be complete? The student used a higher temperature than the others? No, because it decomposed it quicker. The student used less copper carbonate than others? No, because it decomposed it quicker. The student heated the crucible without a lid? Yeah, no, it's not going to work out. It's not reversible in any way, so it's not going to make any difference in the lid design. The student used a spirit burner. Spirit burners didn't get up to high temperatures. So, X energy yield appeared, and guys, we're done. It's very straightforward. Extraction of data for this one. We actually got this. We expected that. Right. That brings me to the end of my calculations. Let's see if we can bring this back. Stop sharing. It's gonna bring me back. Hello. Right, guys. Thanks for hanging around. I know it's been a full hour and 18 minutes. I really do hope it was useful for you. I've done a very quick run through there. I'm still aware that I didn't do the water crystallization as well as I could have. But to do the entire calculations in an hour is always going to be a bit of a rush job. It's definitely worthwhile watching the webinar again if you get time. I hope it was useful. If you'd like a second exam paper to have another go at to see that you're making those improvements, I'm more than happy to create one and send it out at the mark scheme. Just send me an email and I'll do that before the end of the summer holidays. In fact, I'll do it as soon as possible. As soon as I get that email, I will do it. So guys, I hope you have a great rest of your summer. If you want me to do any more webinars, please just give me an email. I know that Aya sent me an email, asked me to do that, and I've done this one really for her. And if you want me to do any others, please let me know, and I will schedule one for you guys to do, for you guys to watch. Guys, have a nice rest of your summer. Take care.